All right, welcome back to the last lesson for this week, where we're going to be looking at how to predict reactions. But before we do that, just a quick little review on the strength of acids and bases. So this once again a little bit from Chem 20, where it's mostly just looking at the difference between weak acids and weak bases, because how we actually classify them from there is going to show up a little bit. Now, besides some of the properties right here, like taste and all that stuff, I just kind of bring your attention mostly to the last three here for strong acids versus the weak acids. Now, for our strong acids, you'll notice that we have a lot of hydronium ions in solution, where the weak acids only have a few. But the main one, specifically, I just want to bring your attention to are the reactions and, of course, the quantity of how many. So when we have a strong acid, it reacts completely with water to form the hydronium, so it is a quantitative reaction. That means that if we have our strong acid, now I'm just going to have strong acid as just, sorry, not SA. Yeah, let's write it. It reacts completely with water to produce hydronium, plus the conjugate base of the strong acid. And there's only a few strong acids here, which once again, if you go to your data booklet, there are the top 6. Now, with the weak ones, these react completely and incompletely, and reaches an equilibrium. So notice how for our weak acids, we're going to use the equilibrium arrow, where the strong acids, specifically with water, we're using the single to form H3O+. So we have an equilibrium here. So that means that, well, that's once again why they're weak, because we're only getting a few of the hydronium ions in solution. Now, this same thing with the bases, except instead of a reaction for the strong bases, these are all metal hydroxides, so they dissociate completely, whereas our weak bases react incompletely. So for a strong base, you're going to see a metal hydroxide, so that's why just MOH, where M is the metal ion. It's going to produce the metal ion and, of course, the hydroxide ion, whereas our weak bases are just going to react, once again, creating an equilibrium. So that means that for our weak acids and weak bases, that there's going to be a mixture of reactants and products there, whereas our strong acids and strong bases, there's no longer any of the original substance left. It's only the conjugate acid and bases that's there. So the reason we kind of want to do that is this is going to tie into a little bit in predicting acid-base equilibria reactions, specifically when we're writing out entities in solution. So just remember, the only significant reaction in an acid-base equilibrium involves the proton transfer, which is just H+, between the strongest acid present to the strongest base. Just like in our our electrochemistry, it was the strongest oxidizing agent to the strongest reducing agent. So the strongest acid is a very, very, very weak proton attractor, so that's why it always donates, whereas strong base is a strong proton attractor. So that is why we get that transfer from strong acid to strong base. Now, we are going to have to go back and remember how to write entities in solution. Now, we did this a lot in the electrochemistry unit, because when we did our 5-step method for predicting reactions, we needed to be careful on how we wrote things in solution. And this is going to be the same here. So we have our types of compounds right here. So ionic compounds, ionic oxides, strong acids, weak bases. Now, our strong acids come in our ionic compounds because they're all metal hydroxides. So you have to remember that if we have an aqueous ionic hydroxide, and you can always check if they're aqueous or not by using the solubility chart in your data booklet. So they're not that way. Solubility chart is right here. So for our hydroxides, all group 1 ions and ammonium. Everything else slightly soluble, so it's not going to dissolve 100%. But if you do have something that is soluble, when you put it in water, what you get are the cations, the anions, and water. So for example, calcium, hydrogen, carbonate. If we put this in water, we get the calcium ion. We're going to get the hydrogen carbonate ion. And, of course, water. So remember, water is always going to be present, of course, if it's in a solution. Now, ionic oxides, we haven't really dealt with these before, but if you do see one, don't worry about it. So an ionic oxide, what's going to happen, we're going to get cations, hydroxide ions, and water. So for example, if we have calcium oxide, what's going to happen is that when we put it in water, we get calcium ions, we get hydroxide, and we get water. So what happens is that for every oxide that breaks off, it just steals, because oxygen is the most electronegative element outside of fluorine, so it just steals a hydrogen from water to create the hydroxide. And there should be more than enough water left over, so that's why we still have H3O plus there. Now for our strong acids, when we put these in water, remember there's only 6 of them, we get hydronium, the anion, and water. So that's where if we have something like nitric acid, HNO3, if we put that in water, the major entities, what we're going to get is H3O plus. Of course, the anion is NO3 minus, and of course, water, H2O. Now, for our weak acids, you have to be very careful about these here. So our weak acids is going to be anything below the hydronium ion line, and there's most of them there. So depending if we have a weak acid molecule or a weak acid ion, when we write them in solution, the major entities, the molecule or ion is going to remain unchanged. So that means HF, if we put this in water, the major entity is still going to be HF. If we put HSO3 minus in solution, then the major entity is still going to be HSO3 minus because they are weak. And of course, water is always going to be present. And this also applies to the bases. Now for the weak bases, if you want to know if it is a base, well, once you go to your data booklet, they are going to be in this conjugate base section right here. So the only one that isn't a weak base, hydroxide, as you know, that's the strongest base. That means everything else on this side of our data booklet is in that base section. So what that means is that if we're given like ammonia, NH3, because that shows up in our base section, it's going to be a weak base because it's not hydroxide, or even this ion, HCO3 minus, same thing, HCO3 minus shows up on this side, so it can be a weak base. If we put any of these in water, they remain unchanged. So the molecule or the ion remains unchanged. And of course, we have water present. So that is how we can tell, or how we write out all of our entities, of course. The rules that we already had before, like molecular compounds, you don't change and stuff like that. So let's look at, well, how can we actually predict equilibrium, or the acid-base equilibrium rule position, before we actually look at the 5-step method. So the relative position of the equilibrium, we need to look at the relative positions of the strongest acid and the strongest base on our acid-base table to use the approximate determination of the position of equilibrium. So what that means is basically we're trying to tell if the reactants are favored or the products are favored. Now we've done this in our equilibrium unit by using the percent reactions, or remember when we had like Kc is greater than 1, so products are favored, Kc is less than 1, reactants are favored. And this is all we're doing here. So in our table, if our strong acid is above our strong base, the products are favored, or the reaction percent is above 50%. So that means, for example, in our data booklet, let's just say you can pick any old ones right here. So I'll just kind of go back. As long as we had something like, if oxalic acid was our acid and it was reacting with, let's say, the hydrogen absorbate ion, we'll notice that acid is above our strong base. So if we actually had 2 of these reacting, our products favored. That's if 2 of those were reacting. Now, if it was the other way around, so if our strong acid is below our strong base, of the 2 things that are reacting, the reactants are favored, or the percent is going to be less than 50%. So what that means, if our base is above our acid, now this combination, reactants are favored. So at the end, this is kind of predicting the spontaneity in our electrochemistry, but we will need to use kind of the tools that we have in our data booklet to figure out if reactants are favored or products are favored for our equilibrium reactions. So let's actually look at our 5-step method to predict reactions, now that we have kind of everything that we need. And one last thing before we do that, if we have H3O plus OH minus, so if you have strong acid plus strong base, it's quantitative. So just be careful with those as well. So there's going to be no equilibrium. So for predicting acid-base reactions, we are going to follow a 5-step method again. Now this is very similar to the 5-step method that we followed for electrochemistry, so really the step-by-step isn't going to be any different. The major difference is that we are going to find our strong acid and strong base instead of strong oxidizing agent and strong reducing agent. So when we look at our first step, it's list all entities, so atoms, ions, or molecules, initially present as they exist in aqueous solution, so following the rules that we have listed above there. So we're going to have to follow dissociation and ionization rules for ionic, molecular, and acids and bases, both strong and weak. So our next step is we're going to identify and label all possible acids and bases using our table of acid and base relative strength on page 8 and 9. So that means that if something is on the acid section, right, you're going to label as an acid if it shows up here. If it's on this side, the conjugate base side, then you're going to classify as a base. We can identify the amphoteric species as both acids and base, right? Now, this you don't really need to do, but it will be handy when you're writing out all of your stuff, is if you see any metal ions, they're going to be treated as spectator ions. And the reason for that, if you check your data booklet on page 8 and 9, there are 0 metal ions present because metal ions will not act as an acid or a base. So metal ions we can just omit. Also, you can omit conjugate bases of strong acids, and they are not going to be included because they are too weak. What that means is that water is right here. This is a stronger base than any of these up above here. So generally nitrate, hydrogen sulfate, chloride, bromide, iodide, and chlorate, we just kind of leave those out as bases. Next, once we list everything as acid or base, we're going to identify our strongest acid by SA and our strongest base, SB present, using our table of relative strength in our data booklet. Now, how we treat strong acids and bases are the same way we treated, the oxidizing agents and reducing agents in electrochem. That means our strongest acid is substance on the top left of our table. The highest substance on the top left side of our table, and our strongest base is going to be lowest substance on the bottom right side of the table. So what that means, as we go up on the left, we have our strong acids, and of course as we go down here, we get our strong base. All right, so that's why when you look at our table of relative strength, the one on the bottom right-hand side is hydroxide, the strongest base of all. So that's how we're going to use that. Now, once we get that step done, we are going to write the equation showing the transfer of only one proton from the acid to the base. And that is it. So we're not going to do 2. If one of the things has 2 hydrogens, that is not going to be the case. It's only going to be a transfer of 1 hydrogen and 1 hydrogen only. So the equation should represent a single proton transfer between 2 entities even when more than 1 proton can be transferred. And last but not least, once we show the reaction, we are going to predict the approximate position of equilibrium using the generalizations that we just went over. So just remember, if you have any of your 6 strong acids or hydronium, that is the strongest acid present and it can exist, so nothing's going to be stronger than that. And same thing if you say hydroxide, that is going to be the strongest entity that can exist in basic solution as well. So if you see any of those, either hydronium or hydroxide, you can almost label it as a strong acid or strong base right away without actually looking at your table. And then, of course, as previously mentioned, if our strong acid is hydronium and our strong base is hydroxide, the reaction is quantitative. Meaning that it goes 100%, so single arrow. So let's look at some of these examples, and that'll be it for this lesson. So, example 1, use the 5-step method to predict the Bronsted-Lowry acid-base reaction that would take place if a student mixed solutions of hydrofluoric acid and sodium sulfate. So, what we have right here is hydrofluoric acid. You could always just double check and see where it shows up in our table. And we'll see hydrofluoric acid shows up down here. It's not one of our top 6, so that means when we write out hydrofluoric acid for entities, the major entities is H, F, A, Q, and that's it. Now we could also write out water, but that's going to be the last thing I write out. Now next we have our sodium sulfate, so this is going to break apart into the sodium ion because it is ionic, and our sulfate ion is SO4, 2-, and because these are solutions, we have H2O. So it's listing all the entities present in solution as they appear. Now next we're going to have to go to our data booklets and figure out which ones are our acids and which ones are our bases. But even before we do that, we can scratch out our metal ion because, as it mentioned up above, metal ions are not acids or bases, they are spectator ions. Now the fact that hydrofluoric acid has acid in its name, we know this can act as an acid. Now as for the sulfate ion, you are going to find that guy on your base section. It's probably on the other page now, isn't it? Yeah, right here. Sorry. Took me a while to find that one. So our sulfate ion is right here. Now you'll notice sulfate does not show up there, so we can classify sulfate as our base. And water can act as both an acid and a base. Now, figuring out which one's going to be the strongest, acid or base, we'll notice in our acid side we got HF up here, which is close to the top left, and water is all the way down here as an acid. So obviously our water, or HF, is our strong acid, so water can't be a strong acid. Now as for a strong base, remember it's the one closest to the bottom right. So as, of course, we scroll up, we'll notice sulfate is right here, water is here, so this is a stronger base. So that can't be a base, and this is our strong base right here. So our reaction, the only reaction there, is going to be the reaction of our strong acid, strongest acid present. So this is our acid, this is our base. So that means we are going to get a proton transfer from the acid to the base. Because these are both weak, it's going to be in equilibrium. We'll be left with the fluoride ion and then HSO4-. And this, of course, is the conjugate base and conjugate acid. Now, this is everything there. The last thing that we need to do is predict the position of equilibrium, and we'll notice our strong base is above our strong acid right here, and as we kind of went before, that means our reactants are favored. So what we would get is a percent less than 50% above the arrow if we wanted to use our percentage stuff. And that is it. So that is the 5-step method for predicting our reactions. Now our next one, I want you to try this one on your own. So it says use the 5-step method to predict a Bronsted-Lowry acid-base reaction that would take place if student mixed solution of sulfuric acid and potassium hydrogen sulfide solution. So just be careful with this one here because our sulfuric acid, remember this is one of our top 6. All right, so that means it is a strong acid. So see if you can do the 5-step method, and we'll have the answer up in 3 seconds. So pause the video and see if you can do this one on your own. Alright, and once you get it done, it should look something like this. So our entities, because sulfuric acid is one of our top 6, we had H3O+, and of course the conjugate base. We had our potassium hydrogen sulfide, and of course our water. Now, of course, our strongest acid present was hydronium. That's why you'll notice I don't have this can act as an acid, just because hydronium is the strongest acid there is. So that means this can act as a base, hydrogen sulfide can act as a base, or water can act as a base. Then when you look at your data booklet, you'll notice that our strongest base there, the one closest to the bottom right, it's down a lot further. It is the hydrogen sulfide, HS-. And then, of course, that right here, our products are favored when you get that reaction. So the last 2 examples on the next page, we have which of the following bronzosyluric acids listed below are stronger than H2S. So this is just using your data booklet. And when you go through, once again, pause the video if you want to fill this in on your own, because I'm just going to put in the answers right now. You will notice that this one is not, this one is not, this one is not, but this one is. Right? So you find H2S in your data booklet, you'll notice that these here are all below. This is the only one that's above. And finally, last but not least, when citric acid. Now, this right here, so if you look up citric acid in your data booklet, you'll notice it has chemical formula right here. Just let me clear off all that. So it has that COOH. So remember, this is a carboxylic acid functional group, and there's 3 of them. So that's indicating that it has 3 acidic hydrogens. So sometimes for complex structures like this, they like to abbreviate some of the ones and go CT. So that just stands for citric acid with the 3 acidic hydrogens right here. So where this one says citric acid combines with water in your mouth, one reaction occur is. So we have our reactants right here. This is our acid and this is our base. That means our conjugate base conjugate acid and conjugate base. So of course, when we're listing out the conjugate acid and base pairs for this reaction, we have our acid H3Ct and its conjugate base H2Ct-, and we have H2O, the base, and the conjugate acid H3O+. And that is it for this section. So using the equilibrium position, and then of course the 5-step method for predicting. Now inside your data booklets, or sorry, not your data booklets, your workbooks, there are a lot of examples of this one right here, so please go over them because being able to use the 5-step method to predict reactions will be very useful for next week when we look at acid and base strength in the equilibrium law, where we are going to be looking at calculating the pH for weak acidic solutions. So you will need to be able to write out the entities and figure out the acid and base reactions from that. All right. So please work on that. If you have any questions, make sure to email me, or please attend the extra help session that we're going to be having on Thursday. But either way, make sure to get lots of practice in, and I'll see you guys either for the extra help session or next week with our last 3 lessons for all of Chem 30. All right, see you guys later.